Hello, everybody. Welcome to Apache MADlib's community call, where we'll be showcasing some of the new features that we have in 1.16, that is Apache MADlib's latest release. I'm Nandish Jayaram. I'm a committer for Apache MADlib, and there's also Nikhil who will be joining me in giving this presentation. He's also a Apache committer. So we released 1.16 a couple of weeks ago. And the agenda for today's community call is we'll first go through we'll have an overview of what we had in 1.16, the features we developed, the bug fixes we made, and one of the main things that we had in 1.16 was introduction of deep learning. So we introduced deep learning in MADlib, which is fully supported by GPU acceleration, and it works on both Postgres and Greenplum. I will go through very briefly about deep learning and also what functions, what MADlib modules we have that support deep learning, and go through a small demo to showcase, the various functions we have and how we can use it to learn some models. And if we have time, we'll also go through some of the challenges that we faced and we solved, and also some challenges that we still face. It'll be really useful if the community kind of looks into it and also can give us more feedback about how to address them. And again, if time permits, we'll also talk about what we have in store for the upcoming releases. So the features that we had in 1.16, as I said earlier, was mainly deep learning focused. So we had a bunch of new features related to deep learning. The first one, of course, being we support deep learning, which is based off Keras and TensorFlow backend. And as I already suggested, it is also with GPU acceleration. So at the moment in 1.16, we only support convolutional neural networks as part of deep learning, not the other facets of deep learning, which we'll hopefully get to in the future releases. And in order to perform the deep learning operations that we can in MADlib, there are a bunch of preparatory steps that have to be done. And in order to facilitate that, we have a lot of utility functions and pre-processing functions that we've introduced, and those are also part of 1.16 release. And apart from deep learning, we of course had a bunch of other things that we worked on, like KD trees, which is another way of performing k-nearest neighbors, but gives approximate solutions. And we also have added support to Postgres. We have a more detailed list of what we have done. Let me quickly go to the link in our release notes. So these are all the features that we've added in 1.16, and these are some of the bug fixes. As you can see, we've done a bunch of bug fixes for MLP, Pivot, and even SVM. And also, there were a couple of minor enhancements that we did, and you could go through the details of this, if you go through the JIRAs here. Just know that there are a bunch of JIRAs associated with deep learning, and you'll have to kind of scroll to your right to see all the JIRA lists, and that these JIRA should have details of what kind of features went into it. And going back to the presentation here, so let's first talk about deep learning. A very, very brief introduction to that. Deep learning is a type of machine learning which was inspired by the biology of the brain. It's not new, it's pretty old. It's been there for decades, and it is kind of an extension of artificial neural networks. So there are some limitations to the design of artificial neural networks, which precluded it from having very deep networks. And deep learning is something that's been done to make sure that we have a much deeper neural network and how we can use that to learn some very complex models. And as I said, we already have multi-layer perceptron in Apache MADlib, which came out a couple of releases ago. And neural networks basically as you can see on the left is a neural network architecture, an example. And as you can see, every node in a layer is connected to every other node in the next layer. And this is a feed-forward network, so there's no cycle back that's happening here. And as you can see, the connections that you see between various the pairs of nodes are the weights that you end up learning in a neural network. And these are densely connected because every node is connected to every other node in the next layer. So this adds up more complexities, like the kind of problems you can solve using the kind of models you can learn using such a network could be limited. So one of the things that is there in deep learning is convolutional neural networks, which is mainly used for image classification. And this is an example. The one on the right is an example of convolutional neural network architecture. And one of the main differences here is the way in which the architecture is connected itself. Not every node, as you can see on the left, every node is connected to every other node on the next layer, but here it's only a subset of the nodes. So the connection is mostly spatially coherent. So if the very first layer was the input layer, which is most often an image for CNN, only subsets of the spatially coherent nodes were connected to the ones on the next layer. So this kind of opened up gateways to learning way more features and way more complicated features that would occur anywhere in the image, unlike a neural network where you would learn a feature as an entire thing over an image and not over sub parts of the image. And there are many other things that are part of CNN. I won't go into the details of this because that by itself could be a very long talk. But this is just an example architecture of what a CNN would look like. CNNs have become very popular. Deep learning became popular in the early part of this century. And then I think about 8 years ago, there was a paper that was published which made use of CNN for and beat out all the existing methods. And since then, a lot of CNN and other deep learning modules have actually been in the limelight. And some of the classic networks that have been developed are LayNet. I think that's pretty old. AlexNet and VGG. VGG is the one that was probably published in 2012, I think. And so these are still some of the complex networks that we have. The whole thing actually kickstarted because of better processing, and the processing was brought about by GPUs. GPUs can perform complex, simple computations really fast, and the simple computations here is mostly like matrix-based operations, and which is mostly what is required for the training of any deep learning or even neural networks. For any of these, it's mostly the matrix operations that you would end up doing to train a particular network. So these are particularly well suited for deep learning algorithms, and the advent of GPUs really boosted the way deep learning evolved. So we do have support for deep learning in Apache MADlib 116 for both Postgres and Greenplum. So the way it would work is all you would need is a Postgres server, as long as you have Postgres installed on some machine, and if that machine has GPU connected to it, and know that you don't have to configure GPU while installing your Postgres database server, but as long as you have a machine which has Postgres server on it, and then GPU is already is connected to it, and if you have installed Keras and TensorFlow, the modules in MADlib 116 should be able to use Keras and TensorFlow as backend to run deep learning modules, and also use GPUs that you have in your database machine for acceleration and computation. So this can very easily be extended to a distributed database, something like Greenplum, where you would have multiple hosts, and as long as each of these hosts have their own installation of Keras and TensorFlow, and if each of these hosts have GPUs connected to them, you again don't have to configure and install Greenplum with all of these together. Just have a Greenplum database setup, and if the machines that the database is installed on have Keras, TensorFlow, and GPU, then MADlib's 116 can be used to run deep learning modules. If you don't have GPUs in either Greenplum or Postgres, you can still run deep learning modules. It's just that it'll be using CPU and it won't be fast enough. So let's go into the interface that we have for running a deep learning module. So MADlib Keras Fit is a training interface, and we assume that it is using Keras backend. And MADlib Keras Fit is only, at the moment, as I said, for CNNs, not for others like RNN. So the first parameter here is basically the input table, which is the training table, which contains all the images that you want to use as training data. The second parameter would basically tell you the output table that you would store the model in. The third and fourth parameters are used to specify what model architecture you want to use. And architecture is what we saw in one of the previous slides of what the CNN would look like. So what that would look like, for instance, if you look at this is an architecture on the right, and you can define that architecture using some code in Python with Keras. And how you would define this architecture, once you define the architecture, you can store it in a table, and that is this table here. The third parameter is that table. And the idea is basically the table could have multiple architectures in it, and which exact architecture you're referring to. So we'll talk a bit more about this, and we'll also have a demo which basically talks about this to give more clarity on what I mean here. The next two parameters are compile parameters and fit parameters, which are also Keras specific. So these are the parameters that we would input to one of the Keras's training functions that's present. And these can be comma separated strings here. And the next parameter is the number of iterations. That's the number of iterations that you want to run your training for. And the next parameter is the GPUs per host. So by default, it is 0. And that means that by default, we end up using CPUs. But if you do have GPUs, and this parameter specifies the number of GPUs that are present in the host. So if it is Postgres, you just have one host, but if you have Greenplum, you could have multiple hosts. And this number specifies the number of GPUs that are there in each of these hosts. And you should, 4 here in a Greenplum cluster means that you should have at least 4 GPUs in all the hosts. And the next parameter is another table which has images in it, which can be used for validation. So we can compute the training loss and accuracy and other metrics, and also the corresponding loss and metrics for test data. And that data can be provided using this particular parameter here. I'll show our documentation here, which basically talks about this. We have a bunch of other parameters like metrics compute frequency, which basically tells you how many times during this entire training process do you want to compute the loss and accuracy for both training data and your validation data. So if the validation table is not provided, then we only compute the training loss and metrics. And we can also do warm start. So if you've already learned a model from somewhere, it could be Apache MADlib's fit function that you've used. And if you've learned a model, you could continue learning from that from wherever you stopped if you have a warm start parameter turned on to true. And these are descriptions that you could have just for better readability of your model table. So one thing guys kind of glossed over here is I told that there is a source table which has images in it, but this source table is supposed to have images which are mini-batched, which are basically batched here. So basically each row in this table is not one image, but multiple images packed into one big row. So we call this big row as a buffer, and each buffer would basically have multiple images in it. So this is a requirement, if you recall from one of our older community calls, this is a requirement that we also have for MLP in MADlib. So the multi-layer perceptron module in MADlib has that's one of the ways you could actually provide input, and to facilitate users to help them create these input tables, we have other helper functions like this one, preprocess of images, where this source table here is one image per row, and this output table would end up getting one buffer per row where each buffer has multiple images in it. And this is the table that you end up giving as input to MADlib Keras's fit function. And the other one I spoke about was the architecture table, where I said that you would have a model architecture thing in it, and we actually have a helper function for that too, where we say, if given an architecture which was represented as, this thing here, given an architecture which basically looks like this on the left, uh, we'll get to more details in demo, but you could convert that into a JSON and upload and put it into the database table, and we can then use this particular architecture table as an input in here. So this is a fit function, a bunch of helper functions to go with fit, and we have other functions like evaluate, which can be used to evaluate the model that you've learned so far on any test data. So if it's not already a data set that you've provided as validation data in your fit function, you can provide a test data as well here. And we also have a predict function which takes in the model table, and then given a new data set, it can actually predict the output for you. And the prediction as an MLP can be of two types. You can either say that you can get the probability of a particular label, or you could get the value of the label that is best, that is predicted to be the output. So these are most of the interfaces that we have. If there are any questions, we can address them here, or we could also address them in the demo. Are there any questions?
So I was wondering the number of GPUs and the number of segments. I guess you want at least one GPU per segment. Is that the case on a host?
Yeah, at least one GPU per host would be required. But I think when you're talking about segments, you're referring to Greenplum here.
Right,
so with Postgres, there's no such case. So you would need at least one GPU in Postgres. But in Greenplum, you could have multiple segments in a host, and so all the GPUs are used by all the segments in a host when we run a MADlib module. So there are some restrictions that Keras and TensorFlow have, which basically say that they might start consuming a lot of resource. So the recommendation is that if you have, say, 4 segments, then it's good to have 4 GPUs. If you have lesser than that, we do try to reduce the load that is taken by each of the GPUs, but I think a more reliable option is to have 4 GPUs if you have 4 segments. Correct me if I'm wrong, Nikhil.
Yes. The recommendation is one-to-one mapping, but we do allow less GPUs. If you have less GPUs than the number of segments, it will work. But in our experiments, we saw that if the GPUs are too low, sometimes it fails. For example, if you have one GPU which has to be shared among 4 segments, then the query fails sometimes.
Yeah.
Okay, thank you.
Okay. Any other questions?
I was just curious, how is the performance difference between the GPU? If you don't have a GPU, I mean, just typically.
Yeah, I think we'd have chats for that.
Yeah, we will come. We'll come to it after the demo. We have a couple of graphs for it.
Okay.
Over to Nikhil for the demo now. Let me stop sharing the screen.
Thank you, Nandish. Hello, everyone. My name is Nikhil. I am also an Apache MADlib committer. And we will quickly go through the demo of most of what Nandish talked about. And if you have any questions during the demo, feel free to ask. There will be some waiting period in between, so I can answer some questions. Okay, so I am running a Jupyter notebook. I'm connected to a GPDB cluster because GPDB is more interesting than Greenplum is more interesting than Postgres when it comes to experiment with GPUs. Because of the MPP feature in it. So right now I'm connected to a 5-host GPD Greenplum cluster, and it has 4 segments per host. And so we have 20 segments and we have 20 GPUs. So there's a one-to-one mapping right now. So let me just connect to my database, and I'm all connected. So the very first thing we have to do is we have to load the images into the database. Right now, we have our own developer scripts that we use to load an image into the table. But eventually, we will have it integrated with an actual product so that it will be easier for users to do it. So right now, we are just using our own test scripts to load an image into the database. It's not part of the Apache MADlib GitHub repo, but we do provide those scripts to the users in the MADlib site GitHub repository, which is this MADlib site GitHub repository. So if you want to try it out, if you want to try something out on your own, you can always come to this.
Yeah, by the way, that is also an Apache MADlib site. So
right, correct. It's just not the Apache MADlib source code. It's just Apache MADlib site. Yeah. Okay. So this is, you don't really need to know how this works under the hood. But what I'm doing right now is our demo today, we will load a Cypher 10 dataset, which is 10 labels and 5,000 images each. So in all, there are 50,000 images that we will train on. And it's a very popular dataset, and you can easily, if you need to know more about this dataset, you can look it up online. So right now what I'm doing is I'm loading the Cypher 10 dataset into a table called Cypher 10 train data and Cypher 10 test data. It will take a few more seconds to load it. So what we assume is that when the user starts training, they will have a table which will have one image per row in their table before they start deep learning, before they call the MADlib deep learning functions. And as I said before, we will eventually have a product which will take in the images from the users and load it into a disk, rather than just having these developer scripts. But that's for future. I'll give it a few more seconds. So the next step that we usually do is, while this is running, I'll quickly run through you the next steps. The next step is we pack the data together. So the output of this is a table which is one image per row. So since there are 50,000 images, let me actually show you the output of this. So if I log into the database and I say select count star from, you will see that it has 50,000 rows. So one row corresponds to one image, all right? Now what we want to do is, before this table is ready to be trained using MADlib's deep learning function, we have to pack the images together. What that essentially means is we want to pack a bunch of images together and then pass that table onto the next step, which is the training function. The way we do that is by calling this MADlib function called training preprocessor DL. And what it does is it takes this source data, which is this Cypher 10 train data, which has 50,000 rows in it, and it outputs this table called Cypher 10 train data packed. This data is a packed version of the other one, the original one. And it has a bunch of other arguments, the buffer size and the normalizing constant. So this module does a few things. It normalizes the data for you. Given the buffer size, it will try to pack all those rows in one row, all those images in one row. And it also one-hot encodes your dependent variable. So I won't run this right now because it takes a while to run this. I'll just show you the output of this. So if you do select count star from this table, you will see that this is much smaller, and this is 50, because each row now contains 1,000 images. Oh, sorry. Let me show you the summary table, which has some more metadata in it. So if I show you the summary table, you will see that the buffer size is 1,000, which was what was passed in. And what this means is one row contains 1,000 images. That's why we have 50 rows, which is 50,000 images in total. And it has a bunch of other metadata in it. And it creates this table called Cypher 10 train data packed, right? This table is the output now. This table now in this pipeline becomes the input for the next step, which is the fit function. Does that make sense so far? Okay. We do this.
So the reason you want to pack is because that's what the image preprocessor requires.
Right. Because we do, the way we train is we do not train on one image at a time. We use mini batch gradient descent inside of CNN. And what it does is it takes a bunch of images in one go and then trains on it, rather than training on one image at a time.
Okay, got it.
Okay, so we do the same operation for validation data. It's the exact same thing, it's just a different data set. it's the validation data set. Okay, so I already have these two tables in my database, so I won't run these two queries. Now the next part is, before we go to the fit function, is how do we define the model architecture? This is what Nandish was talking about when he showed you the image. So let's say you are a user and you have some Python code which defines your model. Now you have to be able to take this model and put it into a table, because MADlib only understands tables. So what we need to do is take this code and somehow put it into a table. The way you do that is you connect to your database. So one of the ways, there are a few ways of doing it, but one of the ways is you make a client connection to Postgres using, let's say, PsychoPG. And then what you can do is you can convert this model to a JSON by doing model.toJSON, and this can be passed into a function called load Keras model. And load Keras model takes in the table name and the JSON and then creates this table with this JSON inside of it. So if I show you, let me run this for you. Oh, sorry, I have to run the previous one. I forgot to run that. And now let me run this for you. And let me show you the output of this table. As you see, it represents this Python code in this Python model in Keras model in a JSON format. And this is what now MADlib would understand. And using this, now we can go to the next stage. The next stage being the fit function. So this is what we have been preparing it all for. This is the actual training. So what it takes is, it takes in the source table, which is the pack table, which is what was this table, which is the output of the preprocessor, which has the data packed. The second one is the output table. This is where the model weights will be outputted to, and this table will later on be used for predict and evaluate. This is the model ask library. This is the table we created in the previous step, which has the JSON, and this ID just is the ID of the model that you want to use. The other two are compile params and fit params. These two are passed in as is to Keras. So we do a couple of Keras operations. One is compile, and the first one is params for compile, and the second one is fit. You can look up more detail on Keras documentation on what these params can be, and you can also look through our documentation to see what kind of params we support. Then there is a number of iterations. The next one is GPUs per host. Right now I'm just saying 2. You can say 4, 5, doesn't matter, but right now I'm just actually I can just say 4 as well. And because right now I have 4 hosts, 4 segment hosts in 4 segments in each host, and I have 4 GPUs available per host. The next is the validation data set. This is what you want to validate your model on, and this is the metrics compute frequency, which means that every 2 iterations we will compute the loss and the metric. So before I get started on running this, I want to show you so that we are actually using GPU. So NVIDIA-SMI is a utility that tells you how many GPUs you have and how much memory each of them is using. So right now, as you can see, we have 4 GPUs on this host. By the way, this is GPDB and this is the master host. I could also go to any of the segment hosts and I will see the same thing. So you can see all of them are using 0 MB out of the 16 GB that is allocated to them. Sorry. Right. So, sorry. Let me run it again. Okay. So as you can see, everything is 0 MB. As soon as I start running the fit function, so if I start this, in a few seconds, it will start using GPU memory. And we will see it just in a few seconds. There is some metadata queries that happen before we actually do Keras fit. So it takes a few seconds to actually use GPU. So the query is running here. Now, since I had said use 4 GPUs per host, you can see all these 4 GPUs are using 15 GB. So a question could be, why are we not using the entire memory? It's because in our code, we only use 90% of the GPU memory so that we can keep some buffer room there. So as you can see, until fit finishes, we will keep using this GPU memory, and then it will take probably a minute to finish this fit function. And as soon as this is finished, so ideally you would think that this memory would be released, but this memory is only released once you log out of that pSQL session. So since I'm logged in to pSQL through this Jupyter notebook, until and unless I log out of this Jupyter notebook, the GPU memory will not be released. So this is one of the lessons we have learned. This is how TensorFlow GPU memory management works, and this is something that you should be aware of while using this module. So the query is still running, and we can see that it's still using GPUs. Yeah, okay, so now it's done. Okay, the query is done. And you can see that there will be the summary table, and so essentially we have trained a model now, right? The next stage is so we have a bunch of functions. So one of the functions you can call is now evaluate. What this function will do is it will take your model that you learned from MADlib Keras fit, and using a test data that was also packed before, it will give you an output table, which is the validate table, and it will tell you how good or bad your model is. So if I run it, this should also use GPUs. I think by default right now this is not using it because we are not passing anything here. So as you can see right now, it says that your model was, so the metrics is accuracy. So this means your model was 38% accurate, and by the end of it, the loss was 1.76. So you could have other metrics here. We chose accuracy because when you look at compile params, you can see the metrics was accuracy. So I think that's it for the demo. Let me go back to the slides. Okay. Any questions about the demo?
I have a question. You mentioned about the memory, that the GPU memory doesn't get released till you exit the notebook. Wouldn't that work also if you just close the database connection?
Right, but how will you close the database connection? Jupyter is holding on to that connection. So if you close it, Jupyter will automatically not work, because Jupyter is holding on to that connection, right? Because Jupyter is connected to it.
I think in Jupyter you can just call like db.close or something.
Yeah, if you do that, you can also shut down your kernel or whatever, and then it will be released. Right. Yes, it will be, yes. But I was just saying that you should be aware that it will not be released until you actually do it.
Right.
Okay, so moving on. So for Cypher, which is a 32 by 32 by 3 image, we saw that GPUs were 2 times faster, but Cypher is not a large image. So there was another image which was places, which is 256 by 256 by 3, and we saw that GPUs were 6 to 7 times faster than CPUs. And this is what the graph is. So this graph only talks about Cypher right now, but if you look at this comment, the 6x, that is more interesting here, because as your images grow larger, the difference between CPU and GPU also grows substantially. Does it answer your question, Shoaib?
Yes, yeah. So I guess the more dense the image is, the better performance you're going to get.
Right, as you would expect, right? Okay. We did some more experiments with Greenplum to see how a 1-segment Greenplum versus 2-segment Greenplum or 4-segment Greenplum would behave. And we found out that in terms of accuracy and training time and iteration, as you can see here, GPU 2 segments was the winner here. So this depends a lot on your cluster, on the way data is distributed, on the way data is, on how big the data is, how many labels you have. So it depends on a lot of things. But right now, this is just Cypher, and we can see the GPU 2 segments outperforms everyone else in this case. Moving on to challenges. So there were a few things that we, while working on the deep learning module, we had to, so these challenges are very focused on deep learning. The first one was TensorFlow memory management. we had to learn a lot about how TensorFlow manages memory, how it releases memory. We had a lot of out of memory crashes and errors, and we had to work around it by creating sessions and whatnot. So there was a lot of learnings around it, and hopefully we will also publish those learnings in our wiki. The second was loading images. Since there was no out-of-the-box solution that we had for loading an image into the database, we had to spend some time on creating some scripts, as you saw, to load an image into the database. Eventually, as I said, there will be a product. It will be an actual product where you can load images, and hopefully then it will be a much smoother experience. There were other challenges, like we had to figure out what the right workflow is. We have a lot of helper functions. We had to figure out the best way for a user to call a helper function, and how we had to strike a good balance between having too many helper functions versus having few helper functions. And the interface itself was also
And if I may comment here, and I think we encourage the community to kind of use this and see how it can be improved, because I think that will be very helpful. Once many people start using it, they would have opinions regarding what is a good workflow, what can be improved, bugs, and even new features that we could work on for future releases. That will be very helpful, I think.
Definitely. More user involvement would be great. We are always looking for feedback. One other challenge we had to work around was the Postgres 1 GB limit. So to be more specific, Postgres has a limitation. So both Postgres and Greenplum have a limitation that a single cell in a table cannot be more than 1 GB. When you call a UDA, the internal state of that UDA cannot be more than 1 GB. So to figure these things out, what we had to do was we had to make sure that the way we serialize our models were serialized in such a manner that they would not take a lot of space. Like obviously, if the model is too big, we can't make it be within 1 GB. But the way we serialize it, we can always avoid it as much as we can. You can look into the Jiras for more details on how we did it. So now we still have a few more challenges to work on. The biggest being the performance. Right now, our UDA could use some more performance enhancements, in that the transition function is, so the Keras fit function is a UDA which takes in one row at a time, and that one row, since the data is packed, is a bunch of images. And it takes a lot of time for Postgres to pass that image all the way to the transition function. We hopefully in the future will try to figure out ways to improve it, and that will make the fit function even faster. Similarly, with preprocessor performance, we hope to improve that as well. Right now, it could use some improvement, and so the preprocessor, I mean, is the one that packs the data together. The other challenges which are more specific to Greenplum are how we deterministically distribute the data, and how we only distribute on a few segments. Because if you have 100 segments, you may not want to use GPUs on all of them. You may only want to use it on like 10 of those segments. So how do you do that out of the box? The other challenges are, so the 1 GB limit is another challenge already. Our models are sometimes inferior when the data is distributed across many segments, and that's pretty obvious. Our accuracy suffers a lot if you have, for example, 100 segments and not enough data. So to piggyback on that, in our future releases, we have a new module called Param Search, which will work on top of MADlib Keras. And what it will do is, instead of so MADlib Keras right now uses model averaging to figure out to combine all the models that are learned across the segments. So this is very Greenplum specific, because Greenplum is MPP, so we have to figure out a way to return a model at the end of each iteration. So what Param Search will do is, instead of trying to merge, it will just circle through all the segments, will see all the models. So what that will do is, our accuracy and our accuracy will not suffer as much. So we will hopefully get better models out of param search. We will go into it in more detail once we have the feature out, and then we can do another showcase around it. And we hope to also have some performance improvements and also officially support Greenplum 6, which is right now in its beta phase. I think that's about it. Are there any questions?
Yeah, I'm just trying to understand the use case. You know, you have Postgres where you can have GPUs. So because we are MPP, we have multiple nodes. What's the advantage the customer gets? Just bigger data sets and
Correct. Like it's the same advantage that Greenplum has over Postgres. At scale, Postgres will not be as fast as Greenplum.
right. So is there any data flow going across nodes then, or is it totally partitioned that you can run process?
No, the data is not. So once the data is distributed, so ideally, in an ideal case, it should never be redistributed while the query is running. And we have not seen it getting redistributed so far. So we don't want it to get redistributed. That's the point, the whole point.
Yeah, that would be good. Okay, good. Thanks.
Okay, I think that's about it. That's all we had. Thank you for coming in and joining us. Please stay tuned. Keep plugged into our user mailing list and our Jiras for more. Thank you, everyone.